So by now you've probably have a few factorization problems under your belt, maybe given some real roots. I wanted to go over one with you where you were given a complex root. So notice right here, this P of I equals 0. That is telling us that one of the roots is x equals I. So whenever you get a complex root, there's a few things we can pay attention to. We would have to take that root and we can use synthetic division to help us figure out the factorization. But you'll notice that the synthetic division isn't as pretty as you've seen in your previous practice. So I want to walk you through that just to kind of ease your mind. And I'll show you what I'm thinking along the way, because it's nearly not automatic. There's a lot of little side steps I'm taking. So I want to model that for you. So let's start off with understanding that if you're given a root, we do have an automatic factor. So I'll kind of keep notes on the side that our factor, in this case, will be x minus I. So we'll kind of work with this. The other important part is that whenever you are given a complex root, there's a theorem, and it's called the complex, what is it called? Complex conjugate theorem or complex conjugate roots. Really, really important, because that automatically tells you that roots come in pairs. Excuse me, not complex conjugate, it's roots. I'm getting mixed up here. This is the conjugate's roots theorem. But all you really have to pay attention to is not the name. It's just that if you have a root, you automatically have a kind of a pair to this. Another root would be the complex conjugate, which is negative I. And we'll get back to that later, but that also tells you that this corresponding factor to this one would be x plus I. So I'll resurface here and again. But the first thing I want to play with is let's talk about using the synthetic division using the complex value. So a k equals I. So let's go with that. And what we'll do is we'll still set up the synthetic division the same. Everything appears to be in descending order, and all the powers of x decrease by 1 as you move from left to right. So I'm just writing out the coefficients, separated a little bit more than usual. So 6, negative 11, negative 4, negative 11 one more time, and negative 10. And I am exaggerating the separation, but you will see why in a few seconds. So just double check we rewrote all the signs correctly. And we have. So I'll draw my bar underneath my synthetic division. And we'll start off nicely. You will see as we pull the factor, we'll notice, not factor, the coefficient beneath the line, we have a 6. Now what happens at this stage? We have 6 times I. So that gives us a 6i above the bar. So this is not a like term with the negative 11. So what we have to do for ourselves is just write it in complex form. So just kind of, they're not like terms, so you have to write them out, negative 11 plus 6i, a little horizontally there. The next step is trying to understand that we're going to have to multiply negative 11 plus 6i times an I. And at this step, if you are reading the textbook, it looks like we just do this in our heads. And I'll tell you the truth, we don't do it in our heads. There's a lot of side work. So I'd like to show that off to the side so that you can kind of work it out for yourself. Really important to just stay detailed. So that's why I like to write off work on the side. So if I'm going negative 11 plus 6i times I, let me write this off. I'll go in blue. So usually it's kind of in an idea monomial times binomial in a sense. And when you do multiply it, you do distribute that I. So you would have negative 11i plus 6i squared. Remember what we said about I squares? I squares are always a negative 1. So what we're looking at is negative 11i plus 6 times negative 1. But if we simplify it, we end up getting negative 11i minus 6. And if you're trying to write it in a plus bi form, maybe you're interested in saying -6 minus 11i. It won't really matter, but I really want to make sure that when you write it, you're making sure that you're rewriting the result above the line. So see how many steps that took? Take your time there. It's really important that we be accurate. So once we have that result of the multiplication, you will add vertically, just taking care so that you're only combining your like terms. So if I'm looking at -4 plus -6 minus 11i, I'm going to combine the constants, the -4 plus -6. So that will leave me with -10 minus 11i. So guess what? We have a new result below the bar. So we're going to also multiply that by our I. So if I do this, again, I'll take it off to the side. So let's take that off. Just kind of change the color off here. I have I getting multiplied by -10 minus 11i. We'll do distribution. So that gives me -10i minus 11i squared. But then we remember that I square ends up turning into a -1. So what we really have for ourselves is -10i plus 11. And if you want to rewrite it so that you have the constant first, the I term second, that's 11 minus 10i. So what we're going to do is write that underneath the next coefficient, but above the bar. And then if we add vertically, we'll notice that the 11s drop out and we are left with -10i. So now we're almost there. We're going to multiply this -10i by I. And this you could do mentally if you'd like. I'll just write it off to the side to make sure. I have I times -10i. So that leaves me with -10i squared. But what's happening with I squared, as we know, it turns into -1. So if we have -10 times -1, we actually have a positive 10. So we can write that result over here. And then look what happens when we add vertically. This is supposed to happen. Guess what? That's the remainder of 0. And that's good. If you get a 0 at the end, that should have been the case because your root, they were telling you, when x is equal to I, your polynomial ends up value being 0. So that's why we're good to go. So that's kind of a check along the way. If you're not getting a remainder of 0, something is wrong. So just check your math. It usually has to do with some negative signs along the way. And that is the reason why you'll see me write my work off to the side of it, just to keep myself organized. Now, you'll still notice that the result of your synthetic division still gives you imaginary factors or imaginary coefficients. So we cannot go straight into our next polynomial factorization until we get rid and we have real coefficients. So what they tell us to do, and this is what I told you I'd get back to, is you're going to apply the conjugate root theorem. And you're going to say, well, if I already did the synthetic division with x equals I, I'm now going to do it with x equals -I. So I'll take this a little further. So what I'll do is I will rewrite the -I. And you could kind of resurface, and I just kind of redraw. You'll see me kind of maybe use a different color just so I know where I'm starting. And I exaggerate a bit. But we're going to perform this all over again. But don't get too scared. You're going to notice some nice things happening. So one more time, we will take this. We're going to take the, I'll do it this way. I'm going to bring the 6 down. Now, when you multiply 6 times -I, you end up getting -6I. When you add vertically, you will notice that your I terms drop out and you end up getting -11. Now, when you multiply -11 times I, you get positive 11i. So if we do this, we get positive 11i that we're writing underneath the next coefficient. When you add vertically, you'll notice that your 11i's drop out and you get negative 10. Repeat, negative 10 times negative I, you will get positive 10i. And this is good news, because when we do get positive 10i, look what happens. They drop out and we get another remainder of 0. And this is exactly what we needed to happen. Whenever we have roots, we should have the remainder of 0. So this is super valuable. Knowing this conjugate root theorem, this allows us to break down this 4th degree polynomial. It allows us to break it down twice, and we now have leading coefficient or coefficients of our next polynomial. So let's kind of take this a little slower and just kind of understand what we did, how powerful this is. We just divided a factor into, so we said x minus I into 6x to the 4th. So we went from polynomial of degree 4. Now in purple, this would be the polynomial of degree 3. If you divide this one more time by negative I, you're going from, see if I can point this out, a degree 4 polynomial to a degree 3 polynomial to finally a degree 2 polynomial. And that's very valuable. So when you write this result, the quotient will in fact be 6x squared minus 11x minus 10. So this is going to be really key in our factorization. So let's kind of go backwards a little bit. I have p of x started off. I'll rewrite it for you just so we see. 6x to the 4th minus 11x cubed minus 4x squared minus 11x minus 10. Knowing what we know about our given roots, conjugate root theorem, we have our factors. So we did figure out I was a root, so x minus I was a factor. By conjugate root theorem, if I is a root, negative I is a root. So by factor theorem, x plus I is a factor. And finally, after we perform synthetic division using both of these complex roots, what we ended up doing is finding a quotient with our polynomial, our remaining factor polynomial, having a degree 2. And if that is the case, what's happening, anytime you get down to quadratic factors, remember, we'll kind of point this out, these are linear factors because the highest degree of those x's is a 1. This is a quadratic factor because the highest power of x is a 2. The moment you have a quadratic factor, you can deal with this using your factorization techniques. So I'll take that quadratic factor off to the side. Do that for myself. 6x squared minus 11x minus 10. And factor it however you like to factor trinomials. I'll use my A times C method. So factors of negative 60 that add up to negative 11. I should have a 15 times 4. Take your time if this doesn't come to you. I usually always experiment with using my calculator and finding the appropriate factors. So 15 times 4, if I'm trying to get a negative 11, I should have a negative 15 and a positive 4. But I have an issue because my A, my coefficient, is not equal to 1. So what I have to do is I take my factors, at least my technique that I just found. I divide both of them by A equals 6, and I reduce. And if I am reducing, I have 15 over 6. Divide out common factors. We should get a negative 5 halves. and 4 over 6 divide out common factors, we should get a positive 2/3. Now using bottoms up technique, I have my corresponding binomial factor. So I should have 2x minus 5. And same thing, 3x plus 2. So we are almost there with the factorization. Part of our work, remember we've got, still have the x minus I, the x plus I. But now this quadratic factor is broken down into 2x minus 5 and 3x plus 2. And so we have this polynomial, 4th degree polynomial factored, knowing some of the complex roots. So I always check to see if I'm done. Use the given root to factor p of x completely. I have. So this would be what p of x is equal to as far as the factorization. But then it wants us to find the remaining roots. So all that means is when you have everything factored completely, just list who are the roots. So you can, we can kind of have a setup here. My roots, in other words, the solution to my equation, p of x equals 0, I do have positive I, negative I, and then to find the other ones, you're just checking out, setting each of those equal to 0. So what do we have? 2x minus 5 equals 0, or 3x plus 2 equals 0. 2x equals 5, 3x equals negative 2. Divide both sides by 2 as far as the left equation goes. So we should have x equals 5 halves. Divide both sides by 3, we have x equals negative 2/3. So we do have our remaining roots. I always like to include all of them, just in case. But you'll notice that you have, right here, we have complex roots, or sometimes we say imaginary. And these are our real roots. And what that means is that you can actually see real roots when you use your TI. You'll see them, those are the clear x-intercepts. Complex roots you will not see. You will only know if someone tells you that they exist or by factoring the polynomials down. So I encourage you practice these problems in the homework. It may seem like a lot of steps at first, but you're really utilizing your concepts of synthetic division, what happens when you multiply complex numbers, and again, factorization comes back once again. So hope this helps, give you some practice. Just take a look at the homework, and I'll see you in the next example.